This is chapter 10 on chemical reactions. This is a pretty math-heavy section out of the chemistry chapters. We're going to be doing a lot with the periodic table, so if you don't have that, you'll want to grab your periodic table. We're going to need to refer to that to get things like atomic weights, and we're going to jump right in. So the first thing to do is work on calculating formula weights. So formula weight is just the sum of the atomic weight of all the atoms in a chemical formula. Pretty straightforward. So we're just going to take the sum of the atoms that are in that chemical formula, add them together, and that gets us our formula weight. So let's just start off with our first one. So we're going to be looking for the formula weight of sodium chloride. So we need to get the atomic weights of sodium and chlorine off of the periodic table. So let's flip over to the periodic table. We're going to find sodium. So sodium has an atomic weight of 22.99. It's okay if you round that up to 23. And then chlorine is over on the other side because we're looking at an ionic compound. We got a metal and a non-metal. Remember, that's how we can tell. And we've got chlorine at 35.45. So if we add those guys together, we're going to get a formula weight of 58.45, or if you're rounding, a formula weight of about 58. So that would be our formula weight for sodium chloride. And that one's pretty straightforward. And so that's formula weight. We're talking atomic weight, so that would be, AMU for atomic mass units. So let's take a look at a slightly different formula. So now we've got hydrogen, H2O, water. This one I actually know the atomic weights for because I use these ones a lot. So hydrogen is 1. Now we've got to look at the subscripts on this one because we've got subscripts. This one's telling us that we've got 2 hydrogens, so we have to add both of those. So 1 for each of those. And then oxygen has an atomic weight of 16. So H2O is going to have an AMU of 18. All right. So then we've got something like sugar. So we've got C12H22O11. So we're going to do something similar that we did with H2O. So you're going to find the atomic weight of carbon. So the atomic weight of carbon is 12. And you're going to multiply that by its subscript. So 12. And we're going to add that to, we know the atomic weight of hydrogen is 1. And if you want to make sure that I've got these right, you can double check it on your periodic table. But again, these are ones that we commonly use, so I've used these guys a lot. Hydrogen, the atomic weight is 1. So 1 times 22 is going to give us 22. And then we have to add in our oxygen, atomic weight of oxygen, 16 times 11. So we get 144 and our 22. That one I can't do in my head. 176. And so then you add them all together for a total of 342 atomic units. Okay. So I've got a couple of other ones here for you to try. So we've got hydrogen peroxide. Yeah, that's the common name. Again, naming rules would be dihydrogen dioxide because we've got this version. So this is a covalent compound. We've got to put the prefixes in front. And then you've got lead nitrate because this is a polyatomic ion. And the thing is, with this guy, you have to take this subscript and multiply it by everything inside of the parentheses. Remember, this is an ion, so it's working as just one single atom. So this subscript outside of the parentheses multiplies against each of these. So there's going to be 2 nitrogens, and you're going to multiply 3 times 2, so that's going to get you 6 oxygens. So keep that in mind when you go to give that one a try. And the answers for these guys are in the notes section of the PowerPoint as always. All right, so that moves us into talking about chemical equations. This is a bulk of the chapter, so chemical equations, chemical reactions. So chemical equations, here we're looking at the creation of carbon monoxide. So carbon plus oxygen gets us carbon monoxide. So we're looking at a couple of different things here. So first we're going to look for the reactants. So who are the reactants in this equation? Well, the reactants are the guys that the arrow is pointing away from, because the reactants are the things that are going to make whatever the reaction is working on. So in this case, we're going to be putting together, and not all chemical reactions are going to put things together. We'll see that later on. But in this case, we're going to put together these two. So the arrow is pointing away from them. So these are our reactants. The other side of the equation is going to be the products, and the products are what the arrow points to, and that's how I always remembered that. The products are pointed to. So the arrow is going to point to the products. In this case, it's carbon monoxide. So the arrow is always going to mean yield or produce. So the arrow points to what's being produced. The arrow points to the products. Now, you might be looking at these guys and wondering, what are these things in the parentheses? What are those for? These are just going to tell you what the states are of the matter that's in the equation, because sometimes this will help you determine what kind of reaction you're looking at. So S for solid, G for gas, L for liquid. We'll see one other one a little later on, and I'll tell you what that one's for. So the direction is going to indicate the direction of the reaction. So if it's pointing this way, that's the direction of the reaction. If it's pointing the other way, that's going to indicate that the reaction is going the other way. So instead of making carbon monoxide, we're breaking down carbon monoxide if the arrow would point in the other direction. So what's with the parentheses? So like I said, state of matter. There's the other one. I knew it was here somewhere. So if you see AQ, that means that the material is dissolved in a solution. So it is going to be dissolved, like you might find sodium dissolved in solution. So you may see, you know, Na plus AQ. What that means is that the sodium is in, for example, water. So the sodium is there, it's just dissolved. So that's what AQ means. All right, so let's take a closer look at our chemical equation here, because we need to talk about the law of conservation of mass. It's been a little while since we looked at this law, but it's back. And so what does the law of the conservation of mass say? Matter is always conserved, right? So what is the problem with the above equation? Because if matter is conserved, that means that matter can't be created or destroyed, right? It just is transferred. So if you look at the above equation, there are equal amounts of carbon on each side, yes, but there are not equal amounts of oxygen on each side. And that violates the law of conservation of mass. The mass of the reactants has to equal the mass of products. We can't just poof destroy an oxygen atom. It has to equal on each side. Okay? So how do we deal with this? We do it by balancing equations. And so you may have done this before, you may have heard of this before. So what we're going to do is we're going to balance this equation so that we're not violating the law of conservation of mass. So how do we fix the equation? Well, we can't just stick a 2 over here because that changes the element, right? So we can't make it just into carbon dioxide because we're making carbon monoxide. So let me erase that so that we don't think later that we are making carbon dioxide. So we're going to fix the equation not by changing the subscripts, so not by changing the lower numbers, because that would change the material, right? So we can't add the 2 here. That'll make it, instead of carbon monoxide, it'll make it carbon dioxide. Completely different material. We also can't take the subscript off over here because oxygen does not exist as a single atom. It can't exist. It will bind with something else. So we can't have just individual oxygen atoms running around. So what are we going to do instead? We're going to use what are called coefficients. Coefficients are big numbers that are placed in front of a chemical formula in order for us to balance the equation. So what we're going to do is, and this is not going to balance this equation, but we're going to write a big number like that in front of the equation in order for us to be able to balance it. Okay? So here's what that would look like. So this is just looking at subscripts versus coefficients. So, we already know that a single letter of the atomic symbol just means one atom. And if we put the subscript in, for example, for oxygen, that means we're going to have 2 atoms of oxygen. And with our chemical equation we're working with, CO is going to tell us that we've got 1 of each. And CO2 gives us 2 oxygen with a carbon. That's why we can't add the subscript here, different molecule. But if we put the coefficient in front, that means that we have 3 CO2s. So we have 3 of this molecule instead. And so that's why we can use these coefficients to help us balance an equation. So this is what the balanced equation would look like for creating carbon monoxide. Now we've got 2 carbons because the coefficient says that there are 2 carbons here, and it says that there are 2 carbons here. We have 2 oxygens because we already had that. And then this 2 is also going to multiply anything in the chemical chemical formula after it. So it also says that we have 2 oxygens. So this is going to now be balanced. In our next lecture, we're going to walk through how to balance equations. If you've not done this before, it's been a long time, I'm going to walk you through how to balance equations, and we're going to do some practice ones.